Welcome to part 2 of training a convolutional neural network on CIFAR 10. We'll pick up where we left off by implementing the model function to be used by our estimator object. The model function contains just that, the full model graph. What's nice is that we won't have to worry about the many non-essential things like plot summaries, logging training progress, and the actual process of running the training steps. That's where the estimator class becomes our best friend because it handles all the stuff that really should be behind the scenes work and makes it happen, well, behind the scenes. We'll spend the last couple minutes of the video showing how to train our estimator model, which the estimator class makes incredibly easy as well. It's time to implement the model function. Let's switch over to our editor and see how it's done. Okay, recall that our model function takes as inputs the batch of features, the corresponding batch of labels, the mode that it's in, which can be either train, eval, or predict. We will only be concerned with train here for quick illustration purposes. And an optional params dictionary. I've chosen to keep params and pass in the batch size of that, and that is entirely up to us. But we should know beforehand what is allowed to be passed in and what's going to be used. Something that should be specified to whoever is using our model if this is used in production as well. First, we do the forward pass of our model. That's why we get the output logits. Note that the logits are the unnormalized outputs, so this is pre-softmax. We'll actually let TensorFlow handle the softmax for us within the loss function, as we'll see. So we compute the loss after the forward pass, we do the optimization and training, and since we're only concerned with the training mode here, we say if the mode is mode keys train, the only option that we'll be using. We specify some training hooks, so this allows us to get some nice print statements. We'll see what these outputs look like. We just want to print the loss for every 1,000 training steps. And we return our estimator spec as seen in the last video and in our estimator template. We pass in the mode, the loss, train op, and training hooks. These are the 3 minimum required arguments here for training. And we also pass in our optional training hooks because we want to see some nice print statements. Alright, so let's move into the first of the high-level functions we've defined here, which is inference. So this is in the CIFAR 10 model file. This function accepts as input the batch of images and also the batch size. This is the diagram that we saw in the PowerPoint slide. We have a few different blocks and abstracted those into their own functions. So remember that we have 2 conv blocks followed one after the other. So let's see first how this conv block is implemented. We need to specify our inputs, the number of filters or output kernel maps we want to use, the kernel size. So let's say if this is 3, then we want to have a 3 by 3 kernel that we're going to be sliding along, and the name for the operation, which can be whatever we'd like. We enter a variable scope for TensorFlow, so that means that all of the variables in here their names will be prefaced with the word convblock or whatever we pass in as name. So they'll have a unique namespace. And we will start with at a high level, we do the conv operation, the batch normalization. Then we do the relu. As mentioned, we slip that in right after the batch normalization as they did in the original paper. And we do max pooling 2D. Note that I have used all of the uppercase versions for the tf.layers. You could also specify relu inside of the conv2D here. That would allow you to not have to use tf.neuralnet, which seems to be slowly making its way out of usage. And we pass in some parameters that are probably familiar by now. In particular, note that we must specify training equals true. Please see the batch normalization documentation for the difference between training equals true and not true. So this is done 2 times. First for the image batch that's passed in. Next for the output of the first conv block is sent to the other one and output. And then we enter our 2 fully connected layers. We make them a little bit different. This is based on the code from the TensorFlow convolutional neural networks tutorial. It does look quite different at this point. I have refactored it, made more modern usage of TensorFlow. The original tutorial was written some time ago. We see how we can specify initializations for our kernel and bias, regularizations, and we will see that how these are used. The L2 regularization is used during our loss computation, and it also makes its way into the optimization. The purpose of this is just to make sure that none of our weights are going driven too high. Okay, and so after our 2 fully connected or dense layers, we pass it to the final layer, which is another dense layer. This time it is output of 10, which is the number of classes we have in our CIFAR 10 dataset. This is called the logits because it is the unnormalized log probabilities. That's an interpretation we heard about in the 1.2 machine learning basics. And that is returned. That is our definition for inference and will be used by the estimator spec that we return in the model function as well. So let's go back to get a reminder of the context here. Given our output logits and labels, we now want to predict the loss. Let's see how that's implemented. As we can see, modern TensorFlow makes this relatively simple for us. We first extract the L2 regularization that we just spoke about by calling tf.graphkeys.regularization TensorFlow places all regularization losses inside this nice little graph keys thing. I encourage you to check out the other graph keys available for easily accessing things like global variables, local variables, model variables, trainable variables, summaries, QRunners, and much, much more. TensorFlow has a nice way of keeping things organized behind the scenes and also allowing us to access them. And lastly, we return the sparse softmax cross entropy function under tf.losses. Note that I encourage you to use the losses under tf.losses. This is the newer API as opposed to the previously used tf.neuralnet or tf.nn. And we also add the L2 regularization loss. The interpretation here is the total loss. This includes the loss from our inference stage as well as the regularization losses. We make our way back to C, where we are at our model function. So now we've computed the logits, we've calculated the loss. All that's left to do is to optimize, or in this case, minimize our loss. And we do that by calling our CIFAR10 model.train method. And this will output the training operation, one of the other things that we need to pass as an estimator spec in our model function. Let's see how the train operation is implemented. We begin by getting the global step variable. This is a nice new handy function I just found called get or create global step. It's nice so that we don't have to pass around our global step variable as we used to do and create it manually. I'm specifying here that the number of examples for each epoch in the CIFAR10 dataset is 50,000 examples. Compute the number of batches for that epoch and how often to do the decay of our learning rate. We assign our learning rate to tf.train.exponential decay, assigned with the initial value of 0.1, decay rate also 0.1, and the documentation for tf.train.exponential decay will tell us how global step and decay steps are used. Essentially, they are raised to the exponent from decay rate, and that determines how fast the decay occurs. We set staircase to true, which means that the learning rate will decay at discrete intervals. Lastly, we grab update ops. This is kind of a safe procedure I'm using when we're working with batch normalization. The old implementation in tf.layers.batch normalization mentioned that we should always do this exact thing here when we're about to compute our training operation. We should grab the update ops, control.dependencies. This means that anything inside of this block here, before it's computed, before TensorFlow runs this portion of the graph, it's going to guarantee that anything inside here has already been run. This ensures that if we're using layers that depend on other layers, perhaps in a less direct way, they have the updated values that they're going to use. The current implementation of batch normalization, the one that we're using, the uppercase version, does not have this warning, but I could not tell from reading through their source code whether or not this was actually protected enough, so this is a better safe than sorry procedure that we're doing here, and perhaps this will be not necessary in newer versions of TensorFlow. And ultimately, we let tf.contrib layers optimize loss handle the optimization procedure. This is saving us a ton of code here. We say that we want to use the gradient descent optimizer. We give it our learning rate in global step, and voila, this is the operation that we need to run to do our backpropagation updates to all of our weights. We now have everything we need to instantiate our returned estimator spec for model function, and once this is defined, we are ready to create our estimator. We can do this in our main function here, so this is the first thing encountered by our program. First, it's going to make sure that we do have the CIFAR10 dataset. It's going to put that in the data directory that you specify from the command line. It's going to make sure that your model directory is clear of any contents before continuing. And here we finally see how we're instantiating our estimator. So we instantiate it by passing it our model function, our model directory, which is optional. We're doing it so that we can have a custom model directory, and also this allows us in future videos to save, load, and restore and export models in a clean fashion. Params is the optional argument to the estimator constructor. For us, we say that param should contain batch size. Recall how we use that in our model function. We use it to inform the inference and train functions what the batch size was. And now we have our classifier ready. So we are truly ready to train, and wow, look how easy that is right there. It is a single call to a single function, as opposed to, 50, 60 lines of code inside of its own method. And all we have to say is, I want to train my classifier. So this is going to first call the model function. It's going to pass in mode as tf.modekeys.train. It's going to build the entire model graph, and then it's going to look at our past input function and it is going to use the outputs of that to feed in the model function and then do the training updates. This is where we see that we can define our input function with any parameters we want, because we're the one actually calling those parameters, and we just do the neat little trick of saying lambda : input function, because the classifier is going to assume that our input function is just a simple callable, as they are said in Python, which means a function that can be called with no parameters. So we can achieve that by just wrapping this in a lambda function. Finally, we specify that we want steps to be 10,000. Now let's see what the outputs of this should look like if everything is set up correctly. I have an example output file here. So I've run /CIFAR10 estimator.py, which is the name of the file. I've said where my model directory is, or where I would like it to be. It doesn't have to be created yet. This is where we're going to be placing all of our output files from training. TensorFlow outputs some interesting logging information, such as my GPU, and this is where the training begins, saving checkpoints for 1 into model CIFAR. It says that we began with a loss of 6 at step 1. It's going to inform us every 100 steps how things are going, in particular the loss. We can choose to put more tensor values in there and evaluate some more stuff every 100 steps. But if I scroll down, remember we started at 6.3 loss or so. After 10,000 steps, I am getting 0.4 loss. And in future sections, we are actually going to see how to monitor and see live updates on plots in TensorBoard, which is a fantastic utility for interactive visualization of our models. That concludes Section 2 on computer vision. We've learned about convolutional neural networks, a handful of the main techniques involved in building such networks, and we saw how to implement our own model in TensorFlow using estimator and tf.data. As always, make sure to read through the links here for an in-depth look at the topics covered today. Coming up next is Section 3 on natural language processing and recurrent neural networks. We'll learn how we can use deep learning to understand and extract meaning from text. I'll see you next time.